Yes, perfectly fine. Hi.
Bonjour à toutes et tous. Bienvenue pour cette soutenance de thèse par Adnan Ali Ahmad. Cette thèse qui a été co-dirigée par Mathias Gonzalez et Patrick Henbel, ici présents, et pour laquelle il y a eu 2 rapporteurs qui sont en ligne, Romain Tessier et Rolf Cooper, et Evelyne Alessian qui est examinatrice ici, présente. Donc en fait, on a 4 membres du jury présents et 2 personnes en ligne. Donc, on va avoir cette présentation en anglais pendant 45 à 50 minutes. Ensuite, on aura les questions par les membres du jury. Est-ce qu'il y a des questions par les gens dans la salle ici ou les gens qui sont docteurs?
La question du président du jury.
On verra si on a. Je me présente, je m'appelle Corinne Charbonnet, je vais présider ce jury. Et voilà, j'espère que je suis sûre que vous aurez autant de plaisir à écouter cette soutenance que nous en avons eu. Alors, je ne devrais pas donner des commentaires tout de suite, mais que nous en avons eu à lire ce document. Voilà, je te laisse la parole. Est-ce que les 2 membres du jury sont Romain et Rolf? Can you hear us? Can you hear well?
Yeah, ready to rock and roll.
Okay, let's go.
Dans les petites thèses. Ok, merci beaucoup Corinne pour cette introduction. Je vais passer en anglais pour les francophones. So, I'd like to begin by thanking the members of the jury, both here with us and on Zoom for attending this thesis defense, in which I will be presenting my findings on the birth of stars, which was 3 wonderful years of research. But before delving into the details of said research, let's first begin by having a closer look at a star that's a bit too familiar to all of us, the sun. So the sun's a fairly typical low-mass star, meaning it has less than 8 solar masses in total. It's a ball of plasma made up of hydrogen and helium with trace amounts of heavier elements, and it's held together by gravity. Now, the immense pressure and temperature at the sun's core causes hydrogen atoms to fuse together into helium, a thermonuclear reaction which releases a tremendous amount of energy. This energy heats the sun and provides it with the thermal pressure support needed to act against gravity, maintaining what we call hydrostatic equilibrium. Now, if you look at the planets of the solar system, you notice something rather peculiar. They all seem to be orbiting the sun in the same orbital plane within a few degrees of inclination. And this led to the famous nebular hypothesis to explain the origins of the solar system by Pierre-Simon de Laplace. Laplace postulated that the solar system was formed through the gravitational collapse of a cloud of gas and dust in interstellar space, which through the conservation of angular momentum led to the birth of a certain stellar disk orbiting a central protostar. Laplace then postulated that this disk is the progenitor of planets, which will form within it and create ring-like structures as they carve gaps by accumulating materials from their surroundings. Now, in order to test this hypothesis, we need to look at nearby star-forming regions in our galaxy. This here is the Eagle Nebula. It's a large cloud of gas and dust in interstellar space, which spans about 60 light years from end to end. In the center of this image here, you have a cluster of massive stars, which has blown away the surrounding gas, and in the process, formed a cavity in the middle. On the edges of this cavity, cold and highly dense gas binds together and forms tight knots. And if we zoom in on one of these knots and switch to a high-resolution instrument, such as the Hubble Space Telescope, we get this image that you've doubtless seen before. It's the pillars of creation, and they're called the pillars of creation because stars are actively forming within them. But we can hardly see those stars because the dust, which makes up about 1% of the mass content of the cloud, is obstructing the visible light that's coming from within. And we can alleviate this problem by switching to the James Webb Space Telescope, which observes at a longer wavelength in the infrared. Here, the veil of dust is significantly lifted, and we can observe many more protostars. But what if we observed an individual protostar? What would we see? This here is a protostar in the Taurus region. It's a star-forming region that's much closer to us. And in the middle of this image here, you have this thin, dark band. It's actually a certain stellar disk that's being observed edge-on, and thus is obstructing our view of the nascent protostar. In the polar regions, we witness outflowing material. It's the magnetic field at the smallest spatial scales, which is propelling the gas to supersonic velocities and ejecting it back into the ISM. So here you can see that protostars provide feedback to their surrounding environments, not only in the form of light, but also mechanically through the launching of these outflows. Now, if we switch to an even longer wavelength instrument, in this case ALMA, which observes in the submillimeter, we notice that most protostars are surrounded by disks of gas and dust, many of which have gaps within them. Remember the nebula hypothesis of Laplace? What we're witnessing here are planetary systems in the making. Now, after observing a sufficient number of these protostars, astronomers began classifying them based on their spectral signatures in what is now known as the empirical sequence. In the cloud zero phase, the protostar is too deeply embedded within the cloud for any of its light to meaningfully escape, as it gets absorbed by the surrounding gas and dust, reprocessed, and re-emitted at longer wavelengths. But over the course of a few dozen thousand years, the protostar will have cleared enough of its surroundings for it to become visible, and we can also notice the presence of a certain stellar disk. And as time progresses, a greater and greater fraction of the surrounding material is accreted by the star and the disk, and the system becomes easier to observe. So it's no coincidence that the best constrained systems, from an observational point of view, are the more evolved ones. And by that, I mean the class 1 and onward ones. Now, after the protostar has finished forming and begun the fusion process, it will enter the main sequence, where it will spend the remainder of its life until it runs out of hydrogen fuel. In the high mass regime, the dying star will go off as a supernova, whereas in the low mass regime, it will simply shed its outer layers into the ISM, forming what is known as a planetary nebula in the process. And in doing so, any elements heavier than hydrogen or helium, which were produced through stellar nucleosynthesis, find their way back into the ISM, where they mix with the original diffuse gas mixture. So the question of how stars are born is not only a quest for our understanding of the origins of the solar system, but it's also an endeavor that will deepen our understanding of a number of astrophysical processes and structures. Now, we've reached the outline of my talk. From here on out, I will first begin by providing you with a theoretical introduction to low mass star formation, which I'll follow with a brief review of the state of the art and a listing of some of the outstanding issues that I've covered during this thesis, namely the angular momentum problem, the magnetic flux problem, the disk mass problem, and the luminosity problem. And after that, I'll present the insights gained by the high-resolution simulations which I've run during my thesis, some of which are still running. And these have led to the publications of 2 papers, with a third one that is currently under draft form and ready to be submitted. Finally, I will conclude and offer you my perspectives for future work. Now, in order to model the birth of stars, we need to consider a number of complex and highly nonlinear physical processes, many of which are simultaneously interacting with each other. And we need to consider these physical processes across a huge dynamical range that spans about 25 orders of magnitude in density and 8 in spatial extent. And when we couple that to the fact that observational data is often limited, owing to the difficulties involved in observing star-forming regions, we very quickly arrive to the conclusion that numerical simulations are a necessity to model the birth of stars. And what these and any such simulation will need to solve a set of governing equations, namely an equation to describe the conservation of mass, an equation to describe the conservation of momentum, and an equation to describe the conservation of energy. Additionally, we have an equation to describe the self-gravity of the gas, an induction equation to describe the temporal evolution of the magnetic field, and a radiative energy equation to describe the way in which the gas and the light interact with each other. Now, what I've shown here are the set of governing equations that I used during my PhD, where I consider the effect of ambipolar diffusion, which is a resistive process that diffuses the magnetic field, and radiative transfer is accounted for under the flux-limited diffusion approximation. And what these simulations have shown is a 2-step evolutionary sequence that results in the birth of a low-mass protostar. Let's suppose that we have a dense cloud core that's gravitationally unstable and about to undergo a collapse, and we're going to follow the evolution of this collapse using this diagram here, which displays the central temperature as a function of the central density, which is here analogous to time. Now, the first stages of this collapse are isothermal, because any of the compressive heating that is generated by the collapse is immediately irradiated away in the infrared by dust grains. But eventually the gas becomes so dense that it's optically thick to its own radiation, by which point adiabatic heating begins. This causes thermal pressure support to go up, and thus forms a first core in hydrostatic equilibrium, the first Larkin core. This core has a radius of about 5 astronomical units, and it's going to continue accreting materials from its surroundings, and in doing so, it contracts adiabatically until its temperatures reach 2000 Kelvin, by which point H2 dissociation begins. Now, H2 dissociation is a highly endothermic process. It consumes about 4.5 electron volts per molecule, and so the gravitational binding energy that was otherwise being injected into the thermal energy budget of the first core is now being spent up by the dissociation process. And as a result of this, thermal pressure support is lost, and a second, much more violent and much more dynamical collapse ensues. And once most H2 molecules are dissociated, thermal pressure support goes up, and a second core in hydrostatic equilibrium forms the second Larsen core, which is the protostar itself. Now, despite the advancements brought by these miracle simulations, there are still a number of outstanding issues that have yet to be solved in the field. And I'm going to begin with the angular momentum problem, which can be boiled down to the following sentence. The sun, despite containing 99% of the mass of the solar system, contains less than 1% of its total angular momentum. And this is a problem because you would expect angular momentum to be a conserved quantity during that collapse. Here you have the specific angular momentum measurement of a number of star-forming objects from dense pre-stellar cores cascading all the way down to fully fledged main sequence stars. And you can see that at each step of this process, angular momentum is lost. And the favorite mechanism to extract this angular momentum is a mechanism known as magnetic braking. Essentially, the magnetic field will resist the bending and twisting motion of the gas and will move angular momentum from high density gas into positive and lower density gas. But the magnetic field has its own problem in star formation, the magnetic flux problem. When we measure the magnetic field strength of dense pre-stellar cores, we have a value that's of the order of 10 microgauss. And the magnetic flux, much like angular momentum, is expected to be a conserved quantity. And should it be conserved all the way down to solar scales, this would yield magnetic field strength in protostars that's of the order of 1 million Gauss. But when we measure the magnetic field strength of young stellar objects, and by that I mean class 1 and onwards, we have a value that's of the order of 1 kilogauss. There's a number of leading hypotheses to explain this discrepancy. The first one states that a magnetic field strength of 1 million Gauss is indeed implanted in the protostar, but that it's subsequently diffused. The second one states that the magnetic field in stars is independent of the initial conditions and is actually generated later on in life through some sort of dynamo process. And the third one is the fossil field hypothesis, which states that the magnetic field is a relic of the second class that's carried over as the protostar transitions from the class 0 to the class 1 phase. The current observational data seems to favor the latter hypothesis. And this can provide us with constraints on second class calculations because it means that they need to be able to implant a kilogauss field strength in the protostar. And in order for that to happen, we would need a magnetic field strength that's of the order of 0.1 Gauss within the first Larsen core and circumstellar disk. And there's a number of indirect measurements that seem to corroborate this value here, namely water maser observations of protostellar jets, paleomagnetic measurements of solar system meteorites, and observational surveys of class 0 and class 1 disk sizes. Now, another problem I'd like to touch on is the luminosity problem. The luminosity of protostars is an important prognostical tool that will allow us to infer how quickly they're forming. And this is because protostars mainly shine by radiating away the incoming kinetic energy of the gas that they accrete at the shock front. And since the interior luminosity of these protostars is quite low, as they have yet to begin the fusion process, the radiative output of protostars is mainly dominated by the accretion luminosity. The diffraction of the incoming kinetic energy that's actually radiated away isn't properly known. And in pre-main sequence evolutionary models, they favor a mechanism known as cold accretion. Essentially, the protostar needs to be accreting low entropy material that has radiated away most of its energy at the shock front. In other words, they need something known as supercriticality, which means that this radiative efficiency parameter needs to be close to unity. But this is an ad hoc statement that is born out of a necessity to confirm their models to observations, and it's not based on any physical analysis of the radiative behavior of the shock front. Now, one final problem I'd like to touch on is the disk mass problem. In larger scale simulations, those that wish to model the birth of star clusters or that wish to describe the long-term evolution of a circumstellar disk, the protostar is often omitted from their calculations in favor of a single particle onto which subgrid parameters are encoded. This is in order to alleviate computational constraints But what's become recently clear in the literature is that depending on the choice of these subgrid parameters, drastically different results can be obtained. And so an adequate description of the star-disk interaction is needed to constrain these parameters. Okay, just to summarize here, we have a number of problems in star formation, which all seem to stem from this common conundrum in the field, in which naive applications of physical conservation laws will yield results that are at odds with observational data. And so carefully and rigorously analyzing each and every process at play is paramount to properly modeling the birth of stars. And one such process, second collapse, will ultimately dictate the birth conditions of the protostar and its subsequent evolution into the main accretion phase. And so it will allow us to gain insights on all four problems listed here. For instance, we can describe the magnetic field intensity and structure that's inherited by the protostar, the amount of angular momentum that it inherits. We can analyze the radiative behavior of its shock front, and we can describe the star-disk interaction. And second collapse calculations go back all the way to 1969 with Richard Larson's PhD thesis, where he carried out second collapse calculations in one-dimensional spherical symmetry. This is where he discovered the first and second cores in hydrostatic equilibrium, hence the names first and second Larson cores. It took 18 years for computers to become powerful enough to make the leap from 1D to 2D, with Scharnöder's 1987 second collapse calculation coming out, in which he was able to study the birth of a protostar in concert with a certain stellar disk. And then it took another 11 years to make the leap from 2D to 3D, with Matthew Bates' 1998 simulation coming out. And I believe at the time, stellar multiplicity was the main focus of the field. Now, what I'm trying to show here is that advancements in stellar formation theory were almost always brought about by leaps and bounds in computing power. Nowadays, simulations are much more advanced. And these two simulations here were the state-of-the-art of three-dimensional grid-based second collapse calculations prior to my thesis, and they include different physics and numerical techniques. The one on the left was led by Vaitin collaborators and came out in 2018. It includes radiative transfer under the flux-limited diffusion approximation. It includes ambipolar diffusion and ohmic dissipation as resistive processes. And they use adaptive mesh refinement, and they have a resolution of 8⁻⁵ AU at their finite level. But this combination of very complex physics with very high resolution meant that they could only simulate 28 days after the birth of the protostar. On the right, you have a different simulation by Mashida and Basu. They're using a nested grid technique. They do not account for radiative transfer. They only account for ohmic dissipation, and they have a much lower resolution of 5.5 and 10⁻³ AU. But this meant that they could simulate for a significantly longer time, 2,000 years after the birth of the protostar. During my PhD, I wanted to carry out a simulation that's similar to this one here, the one by Vaitin and collaborators, but that's pushed significantly longer in time. Now, in terms of scientific results, these studies seem to be reporting the presence of a small circumstellar disk that ranges from 0.1 to 10 AU in size. They tend to report a magnetic field strength of 0.1 Gauss within the first Larson core, but most of them failed to recover the kilogauss field strength in the protostar, with a notable exception of a study by Bursar and collaborators, a smooth particle hydrodynamic simulation, in which they were able to recover the kilogauss field strength, but that required a very high resolution, and it cost them about 2 million CPU hours of calculations. Now, most simulations also report a plasma beta within the protostar that far exceeds unity, which means that the protostar is a thermally supported body. And one final result I'd like to mention is that of Vaitin collaborators, where they measured the radiative efficiency of the protostellar shock front, and they found something that was very much below unity, so a strongly subcritical shock front, which seems to be at odds with pre-mean sequence evolutionary models. Now, I wanted to expand on the results of the literature by running my own suite of second collapse calculations with the RAMSYS adaptive mesh refinement code. These simulations used a combined total of 6.2 million CPU hours, and they generated over 70 terabytes of data, which I had to post-process and analyze in order to extract a physical interpretation from them. And this allowed me to answer a number of questions related to the birth of stars. And the ones that I will touch on during this presentation are the following. what properties does the protostar exhibit at birth and thereafter? How do the newly formed protostar and disk interact with each other? And how do magnetic fields fit into this picture? Very brief word on RANFIS, astrophysical code. It's a code that was developed here at CEA back in 2002 by a woman this year. It's an adaptive mesh refinement code, meaning that the resolution follows the structures that are formed in the simulation. And it's a very robust and very versatile code that has seen a very varied range of applications in astrophysics, ranging from cosmology all the way down to star formation. Okay, so the first simulations I carried out during my PhD were spherically symmetrical collapse calculations. Essentially, I start with a uniform density cloud core that has a temperature of 10 K, and it contains a total of 1 solar mass, and its thermal to gravitational energy ratio is 0.25, meaning that it is strongly gravitationally unstable. The simulation that I'm about to show includes the effects of radiative transfer, but there is no rotation and no magnetic fields. And you might rightfully wonder, why am I using a fully three-dimensional code to model what is essentially a unidimensional flow? And the answer to that is this paper here, which came out back in 2020, and it was led by Adnan and collaborators. It's a very high resolution, two-dimensional second-class calculation, and what you're looking at is the entropy contents of a newly formed protostar. And these swirly patterns here are velocity vector field streamlines. And what you can notice is a significant amount of turbulent eddies within the protostar. And the authors attribute this as being convection. And this is a very significant result because we previously thought that convection in protostars occurs when deuterium burning begins. But here the authors are reporting it 100,000 years earlier than expected. And this convection will lead to very significant entropy mixing within the protostar. Here you can see the turbulent eddies moving the entropy contents of the fluid around. So I wanted to confirm the presence of this turbulence. And so I used a very stringent refinement criterion, which I've coupled with 19 levels of adaptive mesh refinement, going from level 6 to 26. And at the finest level, I have a resolution of 1.4 10 to the minus 4 AU, which is roughly 20,000 kilometers. This yields between 20 to 2,000 cells per gene sign, which means that I have effectively what is the best resolved protostar in the three-dimensional literature. These are the simulation results. What you're looking at is a temperature density histogram, which shows that I'm simulating the two-step evolutionary sequence that I described earlier. We have an initial isothermal phase, the formation of the first core, the dissociation of H2 molecules, and the subsequent formation of the protostar. And this is what the protostar looks like at birth. You're looking at a density slice, and again, the swirly patterns are velocity vector field streamlines, and you'll notice that we have a noticeable amount of turbulent eddies within the protostar. But is this truly convection in the classical sense? And in order to answer that question, we first need to ask, what is convection actually? And convection in stars and protostars occurs when other energy transport mechanisms, namely radiation and conduction, can no longer efficiently carry energy outwards. And what results is a mechanical transport of energy, in which buoyant particles of fluid rise upwards from hotter layers to cooler layers, where they can get rid of their excess energy and subsequently fall back down. And if you do a bit of thermodynamics, you can come up with a criterion for when this occurs, known as the Schwarzschild criterion for instability. It states that for convection to occur in protostars, the entropy gradient has to be negative. So let's take a look at the entropy gradient within the protostar. You're looking at the specific entropy as a function of radius, where each curve corresponds to a different time. Blue curves denote younger times, and red curves denote later times. And what you can see is that the entropy gradient within the protostar is always positive at all times. And what this means is that the protostar is actually stable against convective motion. Now, in order to ascertain where this turbulence is coming from, we need to wind back to the moment of the birth of the protostar. You're looking at a density slice with velocity vector field streamlines, and you'll notice that at birth, the flow within the protostar is mainly radial, and we have very small deviations from perfect spherical symmetry, which are due to our use of a Cartesian grid geometry. This is what it looks like 16 hours later. The central regions of the protostar reach strong hydrostatic equilibrium, and so an outgoing subsonic wave propagates towards the shock front. Now here you can see that those small deviations from perfect spherical symmetry are amplified, but the flow is still mainly radial. And when this wave reaches the shock front, strong vortical movements generate turbulence which permeates the entire interior. But here you'll notice that the protostar is rather pixelated. We're at the finest adaptive mesh refinement level, and so there's a legitimate question regarding the nature of this turbulence. Is it actually physical, or is it some sort of numerical artifact? And in order to answer that question, we can look at the growth rate of the instability. You're looking at the ratio of non-radial to radial kinetic energies within the protostar as a function of time. And what you'll notice is that we have first an exponential growth of this instability, which is then followed by a nonlinear phase that is maintained by accretion. This here is a key signature of a physical instability. And its implication is that since such small deviations from perfect spherical symmetry can generate such strong turbulence within the protostar, then all protostars will be turbulent at birth because star formation does not occur in perfect spherical symmetry. Okay, so I've confirmed the presence of turbulence within the protostar prior to deuterium burning. I've corroborated the results of a previous study in the literature, and in the paper I provide a more quantitative description of this turbulence. And we're still not entirely sure as to what the precise physical instability at play here is, but that will need to be assessed in future studies. And after the publication of this paper, I shifted my focus from protostars to circumstellar disks. Now, in order to model the birth of circumstellar disks, I'm going to be using the exact same setup as before, but this time I include an initially turbulent velocity vector field that is parametrized by the turbulent Mach number. I also consider the effects of solid body rotation, which is parametrized by the ratio of rotational to gravitational energy. And I run a suite of 6 simulations in which I vary the initial amounts of turbulence, the initial amount of solid body rotation, and the ratio of thermal to gravitational energy. Each one of these simulations took over 100,000 CPU hours to complete and between 3 to 6 months of CPU wall time. So now I'm considering radiative transfer, I'm considering rotation, but I'm still not accounting for magnetic fields. Those will come later on. This is the dynamical range that's covered by the simulation. What you're looking at are a set of column density images at various scales. And in the first image here, we have it at the scale of the dense core itself, where you'll notice this filamentary structure that formed as a result of graviturbulence. And it's within this filament that the first Larsen core is born. And in this simulation here, the first core's lifetime was extended enough for a disk to form around it. And it's within this disk that H2 dissociation begins, which gives birth to a central protostar surrounded by a secondary inner circumstellar disk. This disk is rather peculiar. It's quite hot. Its temperature is above 1200 Kelvin, and it's very dense. And in order to ascertain how it formed, we again need to wind back to the moment of protostellar birth. In the top row here, you're seeing slices in radiative flux. Now, radiative flux is an excellent tracer of shock fronts, because whenever you have a shock front, you're going to be converting kinetic energy into radiation. And so you can see this very bright circular outline, which is actually the protostellar shock front. And so here you can see that the protostar is a spherical body at birth. And in the bottom row, I'm showing the azimuthal velocity of the gas, which I divided by the breakup speed, which is a critical velocity beyond which the centrifugal force exceeds the radial component of gravity. And you can see that the protostar is indeed rotating at birth, but it's safely below breakup speeds. This is what it looks like a little over a week later. It's nearly doubled in mass. And with this additional mass came angular momentum. The protostar has spun up. But you can see that it's still rotating below breakup speed. Nevertheless, there's this equatorial bulge that formed as a result of the centrifugal force. And this is what it looks like 2 months later. We have parcels of fluid that exceed breakup velocity, and so material begins spreading outward because of excess angular momentum. And then the sustained accretion ensures that there's a constant flow of material that exceeds breakup velocity. And so what this shows is that the circumstellar disk is actually formed through the rotational breakup of the protostar. And so the accretion shock envelops both the protostar and certain stellar disk because the transition from mainly thermally pressure-supported gas to mainly centrifugally supported gas happens smoothly. And so the two act as a continuous fluid system. Now, I'm going to be showing you just how quickly all of this occurs using an animation, but before showing you this animation, I'm going to go over what you'll actually be seeing. The blue surface is that of the certain stellar disk. The green one is that of the protostar. The white curves are velocity vector field streamlines, and the image panels are cross-sectional radiative flux slices. Take a close look at the time step on the top left. You can see that in over a year and a half, the protostar reaches, the disk, reaches over 0.6 AU in radius, and it just completely engulfs the protostar. And we recover the same structure pretty much independently of initial conditions. Here you're seeing top-down and edge-on views in radiative flux slices, and each column corresponds to a different simulation with different initial conditions. And you can see that we always recover this central flattened protostar that is surrounded by a highly flared circumstellar disk in which it is embedded. And this occurs despite the different evolutionary histories of each simulation at larger spatial scales. You're looking at here the central density as a function of time since the formation of the first core for each simulation. And whenever you see this very steep gradient in central density, that means that the second class has begun. And here you can see that the first core survived for drastically different times in each simulation. It survives for 200 years in some and 4,000 years in others. So at larger spatial scales, very different evolutionary histories are present. But when we measure the resulting properties of the circumstellar disk, here I'm showing the mass-radius relationship, you can see that each simulation follows pretty much the same trend with a very small spread that's due to our use of turbulent initial conditions. And this occurs because of the first Arfman core itself. It's a body that's in hydrostatic equilibrium, and so it halts inward accretion flows until temperatures can exceed 2000 Kelvin, by which point H2 dissociation begins. And since H2 dissociation always begins at a temperature of 2000 Kelvin, the mass accretion rate asymptotically reaches the exact same value, hence the convergence. Now, in these simulations, I'm actually resolving the shock front, and so I can measure its radiative efficiency. But remember that we have this rather exotic structure in which the accretion shock envelops both the protostar and the certain stellar disk, so I'm going to be measuring it at different locations. I shoot out a bunch of rays, 2 rays along the polar regions, which are meant to represent the protostellar shock front, and 2 rays along the equatorial regions, which are meant to illustrate, represent the certain stellar disk shock front. And then upstream of the shock front, I measure the ratio of outgoing radiative energy to incoming accretion energy. And here are the resulting measurements for the polar shock front and the equatorial shock front as a function of time. You can see that the protostellar shock front begins at a very strong subcritical value, but it very quickly reaches unity in the span of about 2 years. So for the very first time here, I've shown that the protostellar shock front reaches supercriticality. And this is thanks to a density cavity along the polar regions that allows the protostar to shine its radiation. In the equatorial regions, we notice that the radiative efficiency also begins strongly subcritical, and it very quickly increases, but it fluctuates around a value of 10 to the minus 3. And so the disk shock front remains strongly subcritical. And so we have an anisotropy in the radiative behavior of the star disk system. And this has implications for the luminosity problem because the radiative efficiency is going to depend on our viewing angle. And it also has implications for the disk thermal structure and multiplicity. Here you're seeing radiative flux slices in a simulation that had a more extended outer disk around the first core prior to the second class. And each column represents a different time. And you can see that as time progresses and the protostar is born, the polar regions become significantly brighter because of the protostar's radiation, but the equatorial regions remain very dark, and this is owing to the subcritical nature of the disk shock front. Okay, so we've obtained quite a few interesting results with these hydrodynamical runs, but we wondered how magnetic fields fit into this picture. So now I'm again going to be using the same setup as before. We have this turbulent dense core, but it's not going to be threaded by a uniform magnetic field that is parametrized by a mass to flux ratio, which is a ratio of gravitational to magnetic energies, which has been set to 4 in this simulation. So now I have radiative transfer, I have rotation, and I have magnetic fields, full physics. I run a set of 2 simulations, one that was run under the ideal MHD approximation, in which I consider that the magnetic field is perfectly coupled to the gas, and one under the non-ideal MHD approximation, in which I consider the effects of ambipolar diffusion. Now, I did account for ohmic dissipation, and this is in light of recent studies in the literature that have modeled the dust size distribution throughout the collapse. And what they found was that owing to the disappearance of small grains within the first Larsen core, ohmic dissipation becomes, well, the ohmic resistivity term becomes rather negligible. And so I consciously omitted ohmic dissipation. Now, these are the results of the 2 simulations. In the top row, you have the results of the ideal MHD run, and in the bottom row, you have the results of the non-ideal run. And you're looking at density slices in which each column corresponds to a different time. Now let's begin with the ideal MHD run. We can see that we form a central protostar that's spherical, and as time progresses, it simply accretes materials from its surroundings, and we have these sort of filaments that are protruding from its surface, but we notice that there is no circumstellar disk in the simulation. In the non-ideal MHD run, well, again, we have this central protostar that forms, but it's significantly larger, and that's because of the centrifugal force. And as time progresses, we notice something that looks like a circumstellar disk with spiral waves permeating it. Now let's take a look at the 3D structure of the system. In the ideal run, we see that what previously looked like filaments protruding from the surface are actually current sheets. These are sort of like coronal mass loops, but just on a much larger scale. And in the non-ideal MHD run, we have something that looks a lot like what we had in the hydrodynamical simulations. A central, flattened protostar that's embedded within a circumstellar disk that formed as a result of its rotational breakup. And the reason why we have these 2 drastically different structures can be inferred from this plot here. It shows the maximum magnetic field strength as a function of time since the formation of the first core, where the black curve is the ideal MHD run and the red curve is the non-ideal MHD run. And you can see that in the ideal MHD run, the maximum magnetic field strength just continuously increases over time until the second collapse. That is because of flux freezing. But in the non-ideal MHD run, you'll notice that the magnetic field strength is actually capped by ambipolar diffusion, which prevents the accumulation of magnetic flux. And so this allows for a reduction in the efficiency of magnetic braking, which allows for enough angular momentum to survive in order to allow the protostar to reach breakup speeds and thus form a circumstellar disk. Now, with regards to the magnetic field strength that's implanted within the protostar, here you're looking at the maximum magnetic field strength as a function of time since the birth of the protostar. You can see that in the ideal MHD run, we have a field strength of 200,000 Gauss that's implanted, but it very quickly diffuses over time. And in the non-ideal MHD run, we have a field strength that's above 10 kilogauss that's implanted, but it very quickly diffuses to kilogauss field values, and it's thereafter maintained. And so ambipolar diffusion allows for the implantation of a kilogauss field strength within the protostar. Now that we've assessed the intensity of the magnetic field, we can have a look at its structure. Here you're looking at magnetic field slices in a top-down and edge-on view, and the white curves here are magnetic field streamlines. And you can see that we have this very strong colloidal component that is threading the disk midplane, and this causes significant spiral waves to appear. And then in the top-down view, we can see that, nevertheless, the field is mainly toroidal. And we can see that the magnetic field streamlines being dragged and twisted by the rotational movements of the protostar and the disk. Now, one final thing that I'd like to mention is the presence of a significant amount of substructure within the morphology of the magnetic field. And this is, again, because of the spiral waves and the turbulence within the disk that sort of reduce its coherence. Okay, now since we're actually describing the smallest spatial scales relevant to the birth of stars and disks, we can describe the star-disk interaction in detail. Now, just a quick reminder here, in larger scale simulations, the innermost sub-AU region is replaced by a sinc particle onto which subgrid parameters are encoded. And the way these sinc particles work is that they will accrete the gas that's within an accretion radius, which is commonly chosen to be 1 astronomical unit. And should this gas exceed a certain density threshold, a fraction of it gets accreted by the sinc particle. And here, since I'm resolving everything that's happening within this radius of 1 AU, I can actually measure the density of the disk shock front and compare it to the commonly used sinc accretion threshold that's used in larger spatial scales. And these are the resulting measurements of the disk shock front, which I've displayed as a function of radius for both the hydrodynamical runs, which is the orange curve here, and then the MHD runs. Now, what you'll notice is that when the disk reaches a radius of 1 AU, the hydrodynamical and magnetized runs yield different results, with the magnetized runs reporting a value that's lower by a factor of 2. But both of these runs report values that are an order of magnitude above the commonly chosen sinc accretion threshold. And what this means is that in larger scale simulations, the masses of certain stellar disks are likely to have been underestimated. And this will deepen a discrepancy in the literature between observations and models. Here you're looking at the cumulative distribution function of certain stellar disks in observations, which is the dotted black curve here, and the models published by Le Breuil and collaborators. And you can see that there's an order of magnitude discrepancy between the two. And what my results are showing is that the model curves should actually be shifted further to the right. And so it will deepen the discrepancy. Well, it worsens the discrepancy that exists. Okay, so we've reached the conclusion of my talk. I've run these high-resolution simulations, and they've offered us a number of valuable insights on the birth of stars. And let's summarize what we've learned so far by beginning with the angular momentum problem. Arguably, the most interesting result of this thesis is the discovery that certain stellar disks are born through the rotational breakup of protostars. Essentially, after the second collapse, the protostar accretes a tremendous amount of material from its surroundings, and with this accretion comes angular momentum. And so the protostar rapidly spins up, and in a matter of months, it reaches breakup velocity. And so material spreads outwards because of excess angular momentum without forming a certain stellar disk. If we prevent this from happening, for instance, by including ideal magnetic fields that very efficiently carry angular momentum outward, this is what we will form: a central spherical accumulation of material that is devoid of any certain stellar disk. Now, if we prevent this from happening, for instance, by including ambipolar diffusion, which reduces the efficiency of magnetic braking, then enough angular momentum survives, and we can allow the protostar to reach breakup velocity, and thus this gives birth to a protostar that's actually embedded within a certain stellar disk that formed as a result of its rotational breakup. So what I'm arguing for here is a paradigm shift in our understanding of the angular momentum problem. Because whatever angular momentum transport process is responsible for spinning down the protostar to the 10–15% of breakup velocity that is commonly observed to have in more evolved systems, then this angular momentum transport process must be acting on longer timescales than the pre-fall time of the cloud, such that it's acting much more gradually and much more continuously than we previously expected. Now, when it comes to magnetic fields, we find that thanks to ambipolar diffusion, the magnetic field strength within the first core reaches a value of 0.1 Gauss, which then allows for the implantation of a kilogauss field strength within the protostar. We also find that protostars are turbulent at birth, and how this impacts the magnetic field, whether it will diffuse it or, on the contrary, amplify it by triggering some sort of early dynamo process, will need to be assessed in future studies. Now, ultimately, unraveling the origins of magnetic field in stars will need a concerted effort in which knowledge from star formation theory, pre-main sequence evolution, and dynamo theory are combined in order to build a cohesive theory that describes the implantation of a magnetic field in a protostar and how it evolves as the protostar transitions from the class 0 to the class 1 phase. Now, we also studied the star-disk interaction in detail, and what we found was that it is strongly dependent on the magnetic field strength that's inherited by the innermost sub-AU region. We saw that the hydrodynamical runs and magnetized runs yield different disk properties, and depending on whether we're using the ideal Amici approximation or the non-ideal Amici approximation, we get drastically different results. And so this highlights the need for better dust resistivities, which in turn will allow for better comparisons between model results and observations. And finally, our resolution of the shock front meant that we could carry out a physical analysis of its radiated behavior. And for the very first time, I showed that the protostellar shock front reaches supercriticality, and this is owing to a density cavity along the polar regions onto which the protostar can shine. But nevertheless, the disk shock front remains strongly subcritical, and so we have an anisotropy in the radiated behavior of the system. And of course, 3 years is not a lot of time in the grand scheme of things, and more work can always be done. Now, my simulations highlighted the benefits of pushing the calculations as far as possible in time, and the holy grail here would be to bridge the gap between the class 0 and the class 1 phase. But this is an immensely challenging task from a technical point of view, and we're going to need to be creative, and we can start by running a suite of simulations with sync particles using different subgrid parameters with the end goal of finding the optimal parameters that best reflect the self-consistent simulations that I've run that can act as a ground truth. And GPU codes can help in that. We can leverage the computing power that they offer in order to push the calculations as far as possible in time. And well, they're rather new, but they're undergoing rapid development, including here at CEA with the Diablo code, which is a GPU-accelerated AMR code. And then from the observational side, of course, we can always get better constraints. Now, using very high-resolution spectroscopy, we can measure emission lines in class 0 systems and try to constrain their accretion properties. And then with longer wavelength instruments, we can, measure the dust emissions at larger spatial scales and thus better constrain dust properties. Now, one final thing I'd like to mention is that with this ever-increasing amount of observational data that's available, we need to better link them with models. And I had this initiative in which I wanted to leverage the hundreds of terabytes of simulation data that are available here at CEA in order to build a data set of synthetic observations of circumstellar disks. And with that, I'd like to thank you for your attention, and I will gladly take your questions.
Merci beaucoup pour cette magnifique présentation.